hope you can all see that. So yes, my name's David, and I'm going to be talking about estimating some microevolution parameters in a social spider. So we talk about evolution as change of phenotypes due to changes in gene frequencies over time. We can think about evolution at different time scales as well. So both at that long time scale, so the macroevolution, so you can get incredible diversity and different kinds of organisms. We can also think about microevolution, and this be the change from one generation to the next. Microevolution is used a lot in the animal breeding world to understand how we can breed kind of better livestock. So how you can go from these small anemic from the middle in the 17th century, and over one generation to the next, you can breed larger cows, cattle, and cows with a higher milk yield, and so on. So we can try and model and then predict microevolutionary change from one generation to the next using the breeder's equation. So this is which lays down that the phenotypic response to selection, so the change in the mean phenotype from one generation to the next, is a product of the selection differential S and the narrow sense heritability H squared. And you can see from this diagram here at the bottom, the selection differential S is the difference in mean between the entire population and then the selected parent, so the individual you choose to breed from. And then you multiply that number, so here would be 2 because it's the difference between 5, the mean of the entire generation, and 7, the mean of the selected parents. You multiply that by a proportion of the variation in phenotypes that's due to additive genetic variance, which is your narrow sense heritability. So if we imagine that was 1, say, then all of the selection differential will be converted into response, and your next generation will have a mean of 7, so exactly the same as the selected parents. Now, in this example, we're imagining that the H squared is in fact 0.5, and so half of the selection differential is converted into response, and so the mean of the next generation will be 6, so an increase of 1. Now, this equation for microevolutionary change is typically applied at the level of the individual. So we can try to understand how populations of individuals are going to be evolving. But there are some cases in the natural world, and particularly among the highly social Hymenoptera, where individuals work together to form superorganisms. And this is idea introduced by E.O. Wilson, among others. And so, and in this situation, it's almost as if these individuals are not individuals trying to maximize their own fitness. They're acting as part of a large body, where the goal appears to be to maximize the fitness of this superorganism, where the reproduction is channeled through perhaps one central organism, which is somewhat representative perhaps of our reproductive organs. So what I was interested in was whether we can model microevolutionary change when you have populations of groups or populations of superorganisms in a similar way to how we might model the evolution of populations of individuals. So my 2 objectives were to try and work out from a theoretical perspective what S our selection differential and what H squared our heritability would be when we're talking about populations of superorganisms rather than populations of individuals. And then I try and estimate these terms in social spiders to provide an empirical example. So first, trying to work out what S the selection differential would be. Now, I actually think this is relatively straightforward. If we can decide what our selected individuals are, and in situations where some sort of superorganisms or some colonies and groups survive and others don't, then we can simply equate the individuals, the colonies that survive to the ones that are selected in the livestock breeding example. And then we can look at the mean trait of the colonies that survive and compare that to the mean of the entire population, and then we can quite simply calculate our selection differential. Now, if we can't separate our population into individuals colonies that are selected or survived and those that don't, we may instead be able to calculate relative fitness if we have some continuous measure of reproductive output, like number of eggs produced or number of offspring colonies founded. Then we can regress this measure of relative fitness on standardized phenotypes to get a selection coefficient, and then we can convert that to a selection differential, allowing it to plug it into the equation. So I wanted to try and estimate this selection differential for social spiders. The picture on the right is terrible, and that's because it's mine. But you can just about see these little red dots with legs, and they're these social spiders of the species Analogous xenos hanging out in a group here. Now, you can get colonies of spiders that are only a single female, but you can get colonies which are up to tens of thousands of individuals. So the picture on the upper left there shows an approximately shed-sized web that probably has tens of thousands of individuals. And they're all cooperating to raise each other's young and to collectively bring down larger prey they would be able to tackle on their own. And the relatedness among individuals within a colony can be over 0.9. So they're almost as closely related to each other as the cells of their body are to each other. Now, we needed some kind of collective or colony level phenotype to measure selection for, and we chose prey attack speed. This is how, when you simulate a prey item being caught in the web, is how quickly the spiders will rush out and try and mob it. And we know that this is repeatable. Different studies get values between 0.15 and 0.38. So we know colonies differ in how willing to attack a prey item they are, for how aggressive they are. And the study that measured these parameters, which I wasn't involved in the data collection side of things, they initially had a hypothesis about how collective prey attack speed would vary according to altitude, and therefore, and how well colonies survive would vary depending on altitude. So they measured this phenotype at different altitudes. So you have to be creative in the field, and you have to be able to construct your modified vibrating device where you can find the local shops. So we did this, and then sometimes these colonies are in hard to reach places. So James Lichtenstein here, who was the lead author on this first piece of work, you can see him here with our vibratory device on a stick, and he is buzzing that spider colony, which looks like a collection of dead leaves in the tree. But you can just about see the webbing there if you look closely enough. And so we start buzzing the colony, and we see how long it takes until the spiders reach out and attack it. We conducted this research in Ecuador, so you can see the map on the left there. We're approximately in the kind of central east area of Ecuador, next to the Amazon rainforest. There's more or less between the towns of Archidona and Tena. Elevations ranging from about 200 meters, just under 1,200 meters. So you can see from this scatter plot, there is a positive relationship between latency to attack and elevation. So colonies with a longer latency to attack are actually more docile. So it's the most aggressive colonies have low values for latency to attack. So you can see that the colonies get less aggressive at high elevations. It's not particularly a strong or particularly certain relationship, but it is there. And you can see there's a natural break in the data at about 600 meters. So to simplify our analysis for selection, we split our data set into low elevation below 600 meters and high elevation above 600 meters. And then, so we wanted to measure survival for these colonies. So what James did was he put tree tags out, and he took GPS coordinates for each of the colonies, and then he returned back to the same colonies in 11 months to determine whether they were still there or not, whether they had living individuals in the colony there or not, and so they survived. And what we found was that at high elevations, above 600 meters, the surviving colonies had a significantly longer latency to attack than the ones that had died, suggesting that there's selection at high elevations for being docile. However, at low elevations, the relationship is flipped, and in fact, at low elevations, they have an average, the surviving colonies have a lower latency to attack, it's just they're more aggressive, although this difference wasn't statistically significant. So we then conclude then that there's selection at high elevations, we can then work out our selection differential. So we can take the mean of all colonies at high elevations, which was 67 seconds it took for them to attack a prey item. And then we can take the mean of the colonies that survived, which are our selected colonies. And that was 54 seconds, giving a selection differential of 13 seconds, which is not particularly large. So that piece of work, aside from the estimate of the selection differential, which is not included here, otherwise you can read about understanding this collective aggressiveness and how it influences survival at different elevations in this paper in the Journal of Evolutionary Biology, led by James. Now then, trying to understand what H squared would be, it's slightly harder. Now, I think that this is most analogous to the mid-parent offspring regression. So the parent offspring regression is a classic method of estimating heritability in animal breeding. And the idea is you regress the offspring's traits. So in the example of these finches on the right here, it's a bill depth and you regress that on the parent phenotype. And you can see here in this example that parent phenotype strongly predicts offspring phenotype, and so there's a very high heritability. And because we only have a single parent in this example, I think it's as if we're using the mid-parent value for our regression. And that means you don't double the slope as you would if it was a single parent. And so you can simply take the slope of this line as your estimate of the heritability. And this is analogous to the parent-offspring covariance divided by the variance in the parent trait. Now, to get the parent-offspring covariance, I think you specifically need to estimate the covariance between the parent and the offspring trait in a multivariate mixed effect model, and you fit a random effective colony identity, which is the same for a parent and offspring colony. And it allows you to separate the among colony covariance from the residual covariance. And this allows you to explicitly determine whether more aggressive parent colonies have more aggressive offspring colonies or not. And this works out exactly the same as an equation by Moritz from paper in 1986, looking at the heritability of group phenotypes, where he had the intraclass correlation coefficient T divided by the probability of inheriting the alleles from one of the parents. So given there's only one parent in our example, that R star is 1, and so the T is exactly analogous to the parent-offspring covariance divided by the parent variance. So my idea here that it's the mid-parent offspring regression or the parent-offspring covariance divided by the parent variance is analogous to previous work. So to measure this, what we did was we measured parent colony phenotypes in exactly the same way as in the previous study. And then we created artificial fission events where we took some spiders out of the colony and placed them 5 meters down the road. We then went back and measured these offspring colony phenotypes to determine whether they were similar to their parents. So we measured the parents 3 times over 6 days, and then immediately after placing them back in the foliage, we measured the offspring colony 3 times over 6 days. And these initial measurements had absolutely no correlation with the parent colony, and you can see that on the graph on the left there. However, we realized while doing this that the offspring colonies in those initial 6 days were regularly moving around in the vegetation. So they were clearly still reacting to the disturbance in some way by trying to solidify their position and build a new colony. So we thought maybe we should wait a little while and allow them to settle down and let the effect of the disturbance pass. So we waited a week and then went back and we measured the offspring colonies another 3 times over 6 days. And this measure of settled behavior does positively correlate with the parent colony aggression, suggesting that more aggressive parent colonies do have more aggressive offspring colonies. And so there's some degree of heritability. Now, the solid black lines in both graphs are the phenotypic correlations. The parent-offspring covariance is extracted from the model as the dashed grey line. Now, in the case on the right with the settled colonies, the phenotypic correlation, the black line, is significantly different from 0, and the dashed grey line does slightly overlap 0, although they're exactly the same strength. I think this is more a lack of power because we only had 15 colonies to estimate this parameter rather than a weak effect. So you can read about that work in this paper, also in the Journal of Evolutionary Biology, with myself and James and other co-authors. So from this, we estimated the parent-offspring covariance as 0.154 and the parent variance as just over 2. And then we get a heritability estimate of 0.07 or about 7%, which is quite small. So we can combine these two. So we have our selection differential of 13, which is the high elevations. And then we have our heritability, which is estimated across all elevations. And unfortunately, we didn't have enough data to be able to estimate the heritability just at high elevations of 0.07. And it gives us a response to selection of just under 1 second per generation at high elevations, which is very small, but essentially says that across each generation, the colonies at high elevations should be taking longer and longer to attack the predator as they're getting less and less aggressive. Now, there are a range of assumptions of the breeder's equation that you should, that can be tested, and if they're found to be violated, they can influence how accurate it is. And I haven't explored thoroughly whether these are all being met in groups of social spiders. So we need to confirm when we're applying the breeder's equation to kind of any example of the evolution of superorganisms, whether the assumptions of the breeder's equation are being met. They're regularly not actually met in other field studies as well on individuals. There's a really interesting paper by Marilia et al. In 2001 investigating why so many predicted responses to selection based on the breeder's equation don't actually match up with the observed response to selection. So ultimately, we know this is going to be a wrong model, as all models are, but it's still perhaps a useful one to probing how we think the microevolution of superorganisms might progress. And ultimately, we need more data of this kind to better explore these questions. So an example, there's a couple of papers on harvester ants from Deborah Gordon's group, who has done an amazing job of measuring the number of offspring colonies a parent colony has over time. So they should have really good measures of fitness. So it'd be interesting to know if they could estimate some of these terms as well. So in summary, it was relatively little explored how evolution at the level of the superorganism might work in the same way as it does at the level of the individual. I've explored whether the breeder's equation can be applied at that level. I collected some data showing a empirical example of social spiders, which ultimately predict relatively slow evolutionary change. So my co-author on these papers I'm indebted to, especially James Lichtenstein, who collected a lot of the data for the first paper and was invaluable in helping me and kept the data with me for the second paper, as well as Hal, Brendan, Justin, Daniel, Esteban, Clara, Yana, and Jonathan, who also helped with either data collection or logistics. I'd like to thank Hannah Anderson and James Barnett, being great colleagues in the field while we were in Ecuador. And I'd like to thank Todd Swanson and the staff at his field station for giving us a really comfortable stay. I'd finally like you for listening, and I'm glad to take any questions.